Okay, so what we're going to be talking about today is we're going to start chapter 17, which is sampling distribution models. And the first lesson, today's lesson, is going to be dealing when you have proportions. Okay, and proportions, remember we do proportions whenever you have categorical variables or categorical data. When there's only two options, you can either have a success or a failure. And so this is when you have a P and a Q, and remember P is success and Q is your failure, and those should both add up to 1 or 100, depending on how you're writing it. Okay, the mean and the standard deviation, these are the two things you have to remember. What's nice is that the mean, when you have a sample model that's dealing with a proportion, it's still just going to be the P. The standard deviation is going to be different though. Standard deviation is the square root of P times Q divided by N. And you have to make sure that it's the square root of all of that. So you have to find the product and then divide by N, and then you take the square root. So we know P is success, Q is failure. Remember, is the N is the sample size. Okay. All right. So we're starting to get into where the conditions and assumptions must be checked, and you can't just say yes, it meets it. You have to describe how it meets it. And so the first thing you have to check is for independence. Okay. And then the second thing is sometimes things may not be independent, but remember that rule, if it's less than 10% of the population, that kind of helps you prove that even if things may not be independent of each other, if it's less than 10% of the population, then that kind of is okay. So this ensures independence. Okay. The next thing you need to do is you need to check to make sure it's random. A lot of times it's going to say that it's random. If it's not random, then you can make a statement saying, assuming that it's random, and then you could proceed, but you just have to proceed with caution, because if it's not random, then it wouldn't actually work. And then the last thing you have to check is you have to check to make sure that there's enough successes and there's enough failures. And that's similar what we did with Bernoulli trials, where if it became a normal model, if you had more than 10 successes and more than 10 failures. Okay? And so again, we're going to focus on proportions, and then we'll check the conditions, and then we're going to follow the process. Okay, so here's the first example. Go ahead and take a second to copy it down, and then we'll go ahead and talk about it. Okay, so the first thing I need to do whenever I see a problem like this, you're eventually going to be working with means and proportions. So I think it's going to be helpful when you say that whenever you have a percent of something, that's most of the time going to be a proportion. So whenever I see that, I'm going to go ahead and tell what my P is and what my Q is right away. Then I'm also going to list my N. So of all cars on the interstate, 80% exceed the speed limit. And what you're doing is it's asking what happens among the next 50 cars. So I'm going to put 50 here. That's the N that I'm looking at. Okay, so we need to check our conditions. The first conditions are, the first condition we have is it independent? Well, I would say, and most people would agree, that yes, cars drive independently of each other. Drivers are independent of each other. Occasionally, you might have a chain of cars that are speeding together, but it doesn't happen that often. And I think because we know that 50 cars is less than 10% of our population of all cars, then we're okay. So those two things together definitely make that this would be independent and it's okay. The next thing is we're going to say, is it random? And I'm going to go ahead and just assume it's random. And so all that means is that if I don't know for sure if it's random, I just have to take caution with some of my results. Okay? All right, and then the next thing we need to do is we need to say whether or not it meets our successes if we have enough. So NP is greater than 10 and NQ is greater than 10. The thing about this is you have to actually show the work. So P is 80 and N is 50. Is that greater than or equal to 10? Well, that's 40, so that works. And then 20 and 50, that's 10. And since it's equal to, it works. So since we have both sets of conditions, all three conditions work, we're good to go. Okay, so what I'm going to do now is I'm going to find my mean, and I'm going to find my standard deviation for my sample. Now I know my mean is P, but the actual notation for it is P hat, which means the predicted mean. And then the standard deviation is going to be the standard deviation of P hat. So my mean stays the same of just 0.80, and my standard deviation is going to be the square root of 0.80 times 0.20, all divided by 50. Now, your standard deviation is going to differ depending on what your sample size is. And so my standard deviation when I plug this in the calculator is 0.057. Okay, so now what I'm going to do is I'm going to draw my normal curve. My mean is 80%, so 0.80. And then I'm going to label 3 tick marks to the right, 3 tick marks to the left. And so when I do that, I get 0.857. And I'm just adding my standard deviations, 0.914, 0.971, and then 0.743, 0.686, 0.629. And so I know that 68%, the bulk of the time, I will get between the first deviations, then 95% of the time, and then 99.7% of the time. Now, what's confusing about this is because I have a percent and then I also have another percent. What this is saying is that 68% of the time, when I have 50 cars, that's my size, I will have between 74% and 85% of cars speeding. So with a sample size of 50 cars, 68% of the time, the number of cars speeding will be, run out of space, between 74.3 and 85.7. Okay, so when there's a sample size of 50 cars, 68% of the time, the percent of cars, and let's just say percent, not the number, the percent of cars speeding will be between 74% and 85%. All right, the next problem says, would it be strange if you got 32 out of 50? Well, we're trying to find out if 32 out of 50 is abnormal. Well, let's do our mean. Here's 80. So I need to figure out what 32 out of 50 is. 32 out of 50 is 64%. So 64% would be over here somewhere. So since it's on the left of the mean, I'm going to go ahead and shade below. And so now I'm going to do my normal CDF. And I'm going to figure out what my values are here. Okay. So I do my normal CDF. My lower, this is a good lower because remember your lower is your left. And then my upper is that 0.64. You also, instead of 0.64, you could just do 32 out of 50. My mean is 0.8. It's not negative. And then we found our standard deviation in the previous problem to be 0.057. So my standard deviation is 0.057. And so 0.0025% of the time someone will be driving, that percent will be speeding. So only 0.25% of the time will that many cars be speeding. And that's a really small percent. So that is really abnormal. It's very rare that that's going to happen. Whenever you have a sample size of 50, then that's only going to happen less than 1% of the time. Okay, so let's look at problem number 2. So go ahead and take a second to copy that down. And then from there, we'll go on and check our conditions and do everything else we need to do. So it says, we don't know it, but 52% of voters plan to vote yes. So 52% are voting yes, so this is a P or Q. So P is 52, Q is 0.48, and we're looking at 300 voters, so that's a much larger sample. So we need to check our conditions. Voters' opinions are independent of each other. $300 is less than 10% of population. It said we took a random sample. Random sample of 300. And then we need to find our success and failure. So 0.52 times 300. Is that greater than or equal to 10? And I'm pretty sure it is because we have such a big number. Yep, and it's 156. And then 48 times 300. Is that greater than or equal to 10? And that's 144. And so since we have more than 10 successes and more than 10 failures, then we're good to go. And so I'm going to cover up the second question again. I keep not leaving enough space. And so we need to find our predicted mean, which stays the same at 52%, and then our standard deviation for our prediction, which is the square root of PQ over N. And so it's the square root of 0.52, 0.48, and 300. So I'm going to multiply those out and divide and take the square root. And so I have a standard deviation of 0.29. Something underneath here I'm writing on a paperclip. Okay, so it says what might percentage be they vote? Well, all you really need to do is say where the middle percent is. So I know that this is 0.52, and one deviation away each is 68%. And so I'm going to add that, and I get 54.9, and I'm going to subtract it. And so this tells me that when a sample of 300 voters is taken, 68% of the time, oops, can't see him. 68% of the time, the voter, they will vote yes. 68% of the time, 49% to 55% of people will vote yes. Okay. So again, it's not saying 68% of the people, it's saying 68% of the time, because you have a lot of different samples, that the people will vote between 49 and 55% will say yes. And I just wrote these instead of writing the whole numbers. I just abbreviated for the summary, which you could do when you're doing summaries. Okay. Next one. The next one, because we've already checked the conditions on a couple, we're not going to check the conditions here. We're just going to make sure we know what we're doing. And so it says 30% of candies. And so that means I have a P, a Q, and then an N. So I'm looking at 250 M&Ms. The question is, when will we get at least 25% of our candies be these new groovy ones that are 30%? So we can talk about the conditions. I'm not going to write them all, but yes, one type of M&M candy is independent of another. We're taking them randomly, and we have more than 10 successes and more than 10 failures. So I need to find my mean for the population, which is still 0.30, and my standard deviation for the population, which is 0.30, the square root of 0.30 times 0.70 divided by 250. And then the square root of that. So it actually is the same square root that we just had. So it's asking, when will we get at least 25%? Well, let's see. My mean is right here, and at least 25%. So that means above that. So I'm going to do my normal CDF. So distribution, normal CDF. My lower this time is that left line, 0.25. My upper, I pick a big number. Technically, if you pick 1, it should work. I don't think the decimals will be that different. So 0.30, 0.029. And so 95.77% of the time, you will have at least 25% of the groovy candies. Okay. All right, and we're not going to do the second one. We don't need to do that second one. That's a different type of problem that I shouldn't have had there. Okay, so when you're doing these problems, remember the first thing you need to do is you need to check for your independence and your less than 10%, and then if it's random, and then success failure, and then you need to do the mean. And so remember, the mean is the P, which is just the P, the probability, and our standard deviation is the sigma of P hat, which is the predicted standard deviation.